Hello everyone. So I'll talk about optimal output sensitive fault tolerant cuts. I'm Niranko Banerjee and this is joint work with Venkatesh Raman and Sakal Saurabh from the Institute of Mathematical Sciences in Chennai, India. So let's start with what exactly is the fault tolerant subgraph model. So what we have is given a graph G, we need to pre-process that graph and store an induced subgraph that is capital H of G such that on some edge deletions or some vertex deletions, which we denote by this term capital F, which means edge falls or vertex falls, so that for any capital F many falls, H minus F preserves some specific property of G minus F. And your specific property may be any of your favorite problems that you can consider. Now, in this case, just to remind that the pre-processing time is important theoretically from a theoretical point of view, but from a practical point of view, type of problems are generally motivated by emergency planning, where you need to deal with some temporary faults in your network or communication by storing a subgraph which is as less of a size as possible, such that the properties are still maintained even if there are some faults. So in that case, the objective is for the upper bound is to find a subgraph H with as few edges as possible. And for the lower bound, you need to kind of show that you cannot have a subgraph with few edges. That does not exist. So those are the objectives. And just to get a flavor of the type of problems that we are talking about, let's say the property is all pairs connectivity in undirected graphs. And so this question means that given a pair x comma y vertex pair, if x and y are connected in G minus F, then they should also be connected in H minus F. Now, if F, the set of edge falls is phi, this is the set of edge falls, right, is phi, then we can see that H is nothing but a spanning tree of G. And the size of H is order n. Now, if you just extend its notion and say that, again, this should be the set of edge falls is the single edge, suppose u comma v, which comes during query time. Now, what is our construction? It's essentially that you pick a spanning tree of G and insert it into H, delete those edges. From the remaining graph, just pick a spanning tree again. And it's not that difficult to see that, first of all, the size of H is 2n, and it's not difficult to see that H is actually a fault tolerant connected subgraph of G. So now let's come into the problems that we considered in this model. The first problem is the problem of global minimum cut, which is essentially a minimum set of edges whose removal partition the graph into at least two components. Then we have a minimum k cut of a graph, which is a minimum set of edges whose removal partition the graph into at least k components instead of two. Now, both these problems are very well known in the statics, very well studied in the static setting. In and around the fault tolerance setting, this problem has also been studied in the distributed fault tolerance setting, as well as the data structure query model in the fault tolerance setting, but not in the fault tolerance subgraph setting. So as far as we know, we are the first to study this. So next, let's look at what is the meaning of the output sensitive nature of our algorithm. Why do we require that? Now note that both these problems actually have quite an easy omega n square lower bound on the size of the subgraph. Why is that? For example, take the problem of global minimum cut. So suppose G is a click on n vertices. Here we have drawn a 4-click, and say an arbitrary edge is not there. Any of the arbitrary edges of the click is not there in H. And for us, say that edge is UV1. Now, suppose now the adversary kind of faults this edge U comma V. It's easy to see that the global min cut in H minus F is actually 1, which is this adjacent edge from U, but in G minus F is actually 2, this and this particular adjacent edge. So you see that if you remove any arbitrary edge from H, the adversary can delete some edge in such a way such that the global min cut of H minus F does not agree with the global min cut of G minus F. So we see that the sizes of G and H has to be the same, which is order n square, many edges. So now, is this the end of the road? So next thing we see that it's not really, because the lower bounds that we consider, the click problem, the global min cut value is actually omega n. Why? Because in a click of n vertices, if you take any vertex and the adjacency, if you remove all the adjacency edges, which is n minus 1, that is actually the global minimum cut. So a natural question comes up that what if we parameterize this problem in terms of the global min cut size? Or in other words, take a fine-grained complexity approach. So we find upper and lower bounds for a size of the subgraph in terms of the global minimum cut size for the global min cut problem, or the minimum k-way cut size for the other problem. Right, so let's just formally define for our problem what is an F fault tolerant global min cut subgraph, in short FFTCS, if it has the following properties for any set F of at most F edges, small f edges, with a global cut value of G minus F agrees with the global cut value of H minus F. And in that, we show the following results. There exists an FTCS with n minus 1 into small f plus GCG edges, and we complement that with a tight lower bound of this much quantity. Now, obviously, we see that this minus and plus values, because GCG can range from say 1 to n minus 1, even this values, depending on the value of GCG, asymptotically, n minus GCG minus 1 can change. So for example, if GCG is something like n minus 1 or n minus 2, or say any order n, then the first value in the lower bound term will dominate, and we'll have an omega n square lower bound, which again agrees with an order n square upper bound. But if GCG is little o of n, then we see that asymptotically this value becomes n minus 1 into GCG plus f, which again agrees with whatever upper bound we have. So we see that the bounds are tight. For the next problem, which we'll just state the results in this talk, is the problem of minimum k cut, as we described before, and a fault tolerant min k cut subgraph FFTKCS. If it has the following property, that Kc of G minus F comma K is equal to Kc of H minus F comma K. And we say that there exists an FTKCS for an upper bound of order n into F plus KCG comma K minus K edges, and we give an almost optimal lower bound as well. For the purposes of this talk, again, I have used asymptotes here, but in our paper, we kind of also try to figure out the constants in our bounds. And as we saw earlier in this version, that the values of GCG or the values of KCG, they also help design the asymptotes for in our results. So that was our results, and now let's give a brief description of our Solutions to the global min cut problem. For an upper bound, our subgraph H is actually pretty straightforward. It's nothing but actually small f plus GCG edge disjoint spanning forest of G. Now this spanning forest, it's just a small abuse of notation that we are doing. Essentially what we mean is, how do we construct H? Take an edge u comma v, and from the graph G, and just find out starting from f1 to f of small f plus GCG, where exactly u and v, the first place where u and v belong to different components, and just go and attach the edge there. In this way, just slowly build this edge disjoint spanning forest, taking edges one by one from G. Now, obviously, it's clear that subgraph H has small f into GCG into n minus 1 edges. And the other property, which is quite helpful, is that given an edge u comma v, which is not there in a subgraph H, by our construction, there are at least GCG plus small f edge disjoint paths between u and v. In H, actually, not in, I mean, G, it's obvious, but in H is what we are considering here. This is by our construction, right? Because if u and v were in different components, it would have been added. So u and v are in the same components in GCG plus f many for us, which results in so many edge disjoint paths. And so now we'll show that H is actually an FTCS of G by showing that GCG of H minus F is equal to GC of G minus F. One direction is simple. H is a subgraph of G. So from there we know that the global cut of H minus F is less than equal to the global cut of G minus F. Now we need to show the other way around. To show this, again, what we do is take a partition capital A comma B of the vertex set of VG, such that, and okay, so this notation I just need to describe. So this is essentially take the partition A, take the partition B in the graph H minus F, and the E of this quantity is nothing but the edges with one endpoint in A and the other endpoint in B. So the cut edges which partition A and B into two different components. This is meaning. And suppose this A and B are those partitions which give you the global min cut of H minus F. Now, obviously, if you consider this partition A and B, and if the edges going through are the same in H minus F and G minus F, then we are done. Why? Because you know, EABH minus F is the global cut of H minus F, which is a cut of G minus F, which is greater than equal to the global min cut of G minus F. Otherwise, suppose there is an edge U comma V, which is there in G minus F, but not in H minus F. But in this case, we know from our earlier observation that due to the construction, there are at least GCG plus small f edge disjoint paths between U and V in H, such that if any f edges are being deleted from even in between U and V, there are at least GCG many edge disjoint paths in H minus F. Now GCG is the global min cut of G. So we have that global min cut of H minus F is at least the global min cut of G, which actually gives the proof that global min cut of H minus F is greater than equal to the global min cut of G minus F as well. So that was an idea of the upper bound of the global min cut problem. I'm not going into the min k-way cut problem. Now let's see the lower bound a bit. So for the lower bound case, what we do is again construct an infinite family of graphs, and we show that from this family, if we try to create any subgraph as our graph subgraph H, then on removal of any f edges, this particular subgraph that we have constructed have to be some minimum size to maintain the required property, in which case, in our case, this is the cut problem. So this is our family of graphs that we construct. So what is this? L here is the global min cut value of G. And suppose we have a click on L plus 1 vertices for this partition x2. And in x1, A1 is the common vertex. And from A1, you have this red dotted edges going to the rest of the vertices, which is n minus L minus 1. And this blue dashed edges, this structures are all clicks on L plus F vertices. So we saw earlier that a simple click on n vertices give an omega n square lower bound. So this structure essentially just plays with the first omega n square lower bound. But in terms of actually inducing this parameters where the global cut size can be anything, which can be any L, and your faults can be in any F, small f. So first of all, again, the global cut, we have defined it as we have defined it as L. The number of edges in G is this particular quantity, n minus L minus 1 into this much plus L into L plus 1 by 2. The L into L plus 1 by 2 comes from this partition x2, and the remaining comes from x1. Now, crucially, this is the property that we use to prove our lower bound. Take any two vertices u1 and u2 in x1. Here, x1, take any two vertices u1 and u2. There are at least L plus F edge disjoint paths between any two such vertices. This is due to the construction. Each of these clicks are of size L plus F, and all of them are connected to A1. Now, this is crucially used because what we now kind of want to show in our lower bound that any FTCS of G must contain all the edges of G, which essentially says that it contains all the edges of this click. And how do we show that? The intuition is that the global cut size will always come from any of the adjacent edges of AI, that is L, but not from any one of them, because as we said that between two vertices here, the minimum number of edge disjoint paths is L plus F. But when F edges are deleted, in the worst case, there may be L edge disjoint paths between any two vertices. In which case, we can show that if we remove an edge from this x1 portion of the graph, the adversary may delete F edges in such a way such that the global cut value of G minus F remains L in this portion, but in H, the subgraph that we have constructed, just by removing any one edge, will become L minus 1. We can take, and we can do so by taking a case-by-case analysis of this entire graph and showing that fact. This shows that any FTCS of G must actually contain all the edges of G. So I would like to end the talk here, and if there are any questions, I am usually free at the time of the talk to take all those questions. And if anyone wants to like offline discuss about the minimum K-cut problem, I'll gladly discuss that as well. Thank you.